Okay, so let's start with the basics. In this video, I want to talk about what we mean by the word probability. Uh, go briefly over the basic ingredients that you'll find in any probability model and go through a quick example. So, on the first point, there's two, I don't want to really say competing, there's two somewhat different ways to interpret the numbers we call probabilities. So two interpretations of a probability. So let me just back up for a minute. In one sense, we use the word probability to talk about a branch of mathematics, like it's the subject of this course is probability theory. Uh, Another sense in which we use the word is a probability represents the number. So the probability that it rains tomorrow is 33%. That's like the number 033. And the two ways that we think about that number, that they're not really inconsistent with each other, but they do sort of put you in different mindsets. One is called the frequentist interpretation, and so you're thinking about that probability as a frequency. Okay, and so sometimes it's a real frequency. Sometimes we're thinking of, okay, like in the last election, 5 out of 6 incumbents who ran were reelected, so the probability that any one of them was reelected was 5/6. Okay, that's so that really is a frequency. How what ratio of the total times something could have occurred did it actually occur? Often the frequencies we have in mind are kind of imaginary. So if it's the 33% chance of rain tomorrow, what am I really saying? I've got however many imaginary universes for tomorrow, and in 33% of them, there's rain. That is often what the models behind forecasts are giving us. We simulated tomorrow 10,000 ways, and in 33% of our simulations, rain rain fell in Santa Monica. So this way of thinking of probabilities in terms of frequencies has some notable advantages. It's very concrete, okay, especially when you get down to frequencies that sort of round to whole numbers, a third, a quarter, a fifth. These are numbers that we can wrap our brains around in kind of a visceral way that is super helpful. And that is not to be underestimated, the ability to sort of visualize, okay, what does 5 out of 6 look like? I mean, literally, if you could get yourself in the habit of visualizing, say, 5 dots or 6 dots rather, with 5 of them colored in, that will help you think concretely about what the numbers that we call probabilities are actually saying. On the other hand, this imaginary frequency and 33% of the possible worlds that could occur tomorrow, if you start thinking deeply about it, it's really, really weird, and you don't want to get too attached to that. Okay, so there's taking a sort of a moderate approach to frequencies is what I would advocate. They are super useful, but remember, it's a useful fiction many times about these frequencies. The maybe more reasonable, but sometimes less useful interpretation of a probability is what we would call the subjectivist interpretation, and it's kind of a no BS approach. Probabilities are numbers that represent how likely we think something is to occur. End of story. Okay, no mumbo jumbo about you know what fraction of the time and how many imaginary universes something happens. It's just a number. We're going to see in the very next lesson. It's a number has to be between 0 and 1. Closer it is to 1, the more likely it is that we think something happens. The closer to 0, the less likely it is. Okay, so this to me is the more plausible, believable at the roots way to think about probabilities. They are just numbers that help us communicate with each other how we're thinking about things that are uncertain. Okay. One other kind of preliminary comment on talking about probabilities, how we do it in probability theory and how we do it in ordinary life. Um, you noticed in my little examples here, I'm talking about probabilities as particular numbers, and that is the way probability and probability theory works, okay? It's not inconsistent with, but somewhat different from thinking about probabilities as odds. Okay, that's an older way of thinking about probability. And as I say, it's not inconsistent with modern probability theory, um, but it's not the most useful frame for doing the making the kinds of arguments that we want to make. Okay, so just thinking about how the probability numbers that we're going to be talking about in this class relate to odds. We might say something has 2-to-1 odds. What we're thinking about there are the ratios of probabilities. Okay, so what we're saying is that if X happens with 2-to-1 odds in favor of it, X is twice as likely to occur as not. Okay, so what we might be saying is that the probability of X is it's the ratio of the probability of X. I'm getting ahead of myself with some of the notation, so I'm going to go back and be much more systematic, but might as well give you a preview of where we're going. The ratio of the probability that X happens to the probability that X doesn't happen. So that's what that little C up there is telling us, that this is X not happening here. If we say that that is 2, what that is saying is that the probability of X is 2/3, and the probability of not X is 1/3. And the reasoning behind that is going to be clear 2 lessons from now. Maybe it's clear already. Okay. I don't want to, here again, I'm trying to send a nuanced message, kind of a middle ground. There are parts of, there are statistical techniques that you may use, that you will certainly see other social scientists using, where people do conventionally talk about their results and their findings in terms of odds ratios. It's a minority, though. The more common way to think about our results is just in terms not of the ratios, but of the numbers that make them up. There's variation across people as well. If you're used to thinking in terms of odds, people who are like really into spectator sports and following them in sort of a betting sense, I think can be very comfortable with talking about odds. That's fine. If you've got facility with something, it's not going to be wrong. You're not going to, if you are correctly making the transition from talking about odds to talking about probabilities, you're not going to, get inconsistent results. If you're not already comfortable with thinking in terms of odds, I would say for this class, don't worry about it. For this class, really, it's the probability numbers themselves that probability theory is based on, and that they provide the foundation for the statistical techniques that we're going to be using. Okay, so just as kind of a segue here, some basic nomenclature, I want to segue into kind of the ingredients in a probability model. And one thing I want to say at the outset is we use probabilities in the context of models, okay? We use them to say things that we think are true, might be true, somebody else thinks is true about the world. They are simpler than the world. They are in one sense made up, okay? It's our model, we decide what to focus on and what to leave out, but we're social scientists, we're trying to make up our models in ways that are honest and accurate and reflective of reality. And in particular, we can also test with data, okay? So I'm putting this kind of cautionary note out here early, and I'll probably touch base with it a couple times in the classes, because it's easy when you're learning probability, we get into kind of a frequentist mode, like there is this true probability out there that we're going to discover. And that, again, it's a useful fiction. It can help us to think about moving towards that. But in reality, we're really just trying to talk about what we think might be true in a way that's systematically enough that we can talk to each other without arguing past each other. All right. So probability models are based on these things, on we're going to be calling the probabilities of events. So let's go on and talk about the 3 ingredients in a probability model. Okay. So as I talk through the definitions or the lingo, I'll use everybody's least favorite probability model, but it's helpful because it is so boring. It's not going to distract us from the basics, and then we'll do an example with a slightly more interesting political example at the end. Okay, so one ingredient is the sample space. If we're talking about a probability model, like what are we talking about? What's the set of things that can happen? Okay, the set of possible outcomes. So here's the boring example. Woohoo, let's flip 2 coins, and the sample space, which we almost always call S, would be a set with these elements, HH, HT, TH, and TT. Okay, those are the possible outcomes if I flip my coin 2 times. When we're starting to set up a model to talk about what we think is accurate about something that's uncertain, one of the things that we want to get straight right at the outset is, well, what is the set of possible things that can happen? Okay, so here's my set here. Okay, and okay, so this is ingredient 1. Ingredient 2, what are we talking about? Okay, so an outcome here in this example would be 2 heads. I'm just writing it like that. The third ingredient in the foundation of any probability model is defining events. Okay, and an event can be an outcome, but it can be more. The event is the thing that we care about. The event is what we assign probabilities to. Okay, so an example of an event could be this one, HH, HT, TH. In ordinary language, we might call that event at least 1 head. Okay. Another possible event, let's call it F, could have a single outcome in it. Okay. So the events are the outcomes are the set of all possible, the outcomes are the things that can happen. The sample space is the set of all possible ones, and the events are the things that we care about. Okay, so how we define events very much depends on like the questions that we're asking here. But a very important point about events that you might notice here is I'm putting the curly brackets on them. That's telling me that events are sets. Okay. So I'm not done yet, but I am going to nonetheless look ahead to the next lesson. The next lesson, we're going to do a quick overview of set theory. Set theory is important for probability theory because we represent the things that we're assigning probabilities to as sets. So we need to know a little bit about sets to have a mathematical foundation there. Okay, so let's do one more quick example here of these ingredients in a probability model. So these are, I guess I should say these are 3 of the 4 basic ingredients, and maybe I'll go back and write in the 4th one here. The be what we might call probability law or probability function, the thing that assigns the probability numbers to the events. So let's do an example here where the outcome of interest is government in parliamentary system. Okay, so I'm thinking about the kind of situation that occurs in most European countries, kind of most of what we sometimes think of as advanced democracies, except for the US, systems where the head of government is elected within the legislature, not separately as president. So just kind of a little bit of basic comparative politics there. So in a parliamentary system, the legislature elects a government, and in particular, we're going to think about a system where there's not necessarily a single majority party. Okay, so in this example, we're going to have three parties: Party A, Party B, and Party C. And let's say there's been an election and Party A's got 40% of the seats, Party B's got 40%, Party C's got 20%. So no single party can form a government here. Probably going to have a coalition government, although not necessarily. That's going to be in the model too. And we just want to be thinking about what's going to happen. So this is a situation of political uncertainty that arises regularly in many countries. Okay, so let me actually start with outcome rather than sample space. Okay, outcome is going to be a government characterized by the parties. Okay, so sample space is going to just list all the possible governments. Okay, so one could be a coalition party, a coalition government of Party A and Party B. And what I'm going to do here is, in representing the outcomes, denote them with small letters here. So let's just, this is trying to get my red pen here. This is a coalition of A and B. Okay, we could also have a coalition government of A and C. We could have B and C in coalition. What else could we have? Well, sometimes those would be probably the most likely outcomes, but sometimes we have national unity governments. Sometimes all the parties get together and decide that they're going to support government. Doesn't happen all that often. I think of it as something that maybe happens when the country's like threatened militarily or something like that, but it's not impossible. The other thing we could have, and that some countries have with some frequency, is a minority government. Okay, we could have just Party A by itself. Now that's going to be a different kind of government because it's only got 40% of the seats in the legislature, but minority governments are quite common in some places. They're reasonably common in Canada. The Scandinavian countries have had them for prolonged periods. So we could have a minority government of Party A, of Party B, and Party C. Okay. That's my sample space. Okay. For an example of an event here, we might want to say Party C is in government. Okay, so that would come from the question that we're motivated by. Like if we're trying to assign a probability, what's the probability that Party C is in government, gets a ministry, gets some say in policy? That would be an event. And this is an event that has several outcomes in it. Okay, so let's call it event C, capital C here. So notice I'm using capital letters both to denote the parties, but also to denote events here, and little letters, lowercase letters, to denote the outcomes. The ways that C can, the outcomes that comprise the event, C is in government, the ways that it can happen, well, C can be in a coalition government with party A or party B. C can be part of that national unity government, or C could be in a minority government by itself. Okay. 2 comments. That's kind of really all I want to do with the example right now. We're going to touch base with it a couple more times once we get a little bit further in talking about probabilities. But the thing that I want to note right now, if you're interested in government formation in these kind of countries, you might be thinking, well, this is, yes, the set of possible governments that could form, but it's not exactly the set of things that can happen after an election. Another thing that can happen is like no government forms. It's called a crisis. This can go on for a long time. Belgium in particular has had some really long crisis periods. Do we want to include that possibility in our sample space or not? And I'm bringing up this point because the answer is important. The answer is, it depends on what we're trying to say. Again, that this is a model. Okay, there's no like absolutely right answer or absolutely wrong answer. What matters is that we're transparent at the beginning about what our sample space is, that we are explaining it accurately to the people we're talking to, that we're keeping it consistent in our own mind. Okay, so even something as seemingly cut and dried as like what's a sample space, what's an outcome, there's judgment in there. And the point of expressing your ideas and your judgments through probability theory is to make clear, you know, what the limits of your model are, what things you're choosing to focus on, what you're not choosing to focus on. Okay, so back to this example, if this was part of a model that really was about, you know, parties being in government and invested governments making decisions and things like that, I don't think I would put the non-government, crisis in there as an outcome. If what I was trying to explain is post-election politics and what happens after an election that doesn't produce a single party majority, then I might. Or then I might think about, you know, other dimensions of the sample space. So going forward, we're going to be learning probability in the context of little toy examples where I'll say, suppose all of these things are true and we know that they're true. That's helpful for us while we're learning to translate ideas about the world into mathematical models. Okay, and so when you're doing a problem in a probability course, yes, there's a right answer and a wrong answer for what the sample space is. When you're doing real research, there's less of that. Okay, and that's either something to look forward to and with enthusiasm. I hope that that's your attitude, or to be a little bit intimidated by. There's a little bit of realism there, but you guys are going to be ready very shortly to be using the tools of probability to express your own ideas. Okay, so that's a good overview of the basics. Our next lesson is going to be an overview of set theory. And again, we're going to talk about set theory because the things that we assign probabilities to are sets. So I'll see you then.